my dear student, colleagues, and all the viewers who are watching this program live from Facebook page. I'd like to welcome you all to our International Physics webinar. And today it is our 32nd Physics webinar. So good afternoon to all here in Bangladesh and good morning to all those who are watching this program from Switzerland. Hope you are well and safe from Corona pandemic. All we know that we are passing very bad time. We are living in a Corona pandemic situation and we cannot continue our normal academic program due to the Corona pandemic situation. So we have to start online program. So you have already come to know that our Department of Physics, Pabna University of Science and Technology, has started some online program like online classes and online international physics webinar. And I'm happy to share with you that today it is our 32nd physics webinar, and you'll happy to inform that in those physics webinars, the physicists from different countries are coming as a main speaker, and they share their experience with our student, and they deliver their speech. And I think by this way, students are benefited. So the main aim of our program is to motivate and encourage our students in this Corona pandemic situation. So today, actually, I would like to welcome you all to a joint session between our university, Pabna University of Science and Technology, Bangladesh, and the Department of Theoretical Physics, CERN, Geneva, Switzerland, in a particle physics and cosmology. And we have here with us today Dr. Valerie Domcke, faculty member, Department of Theoretical Physics, CERN, Geneva, Switzerland, and EPFL, Lausanne, Switzerland, joining us from Switzerland. So she has already connected with us. So I'd like to welcome her in our webinar. So, Madam, good morning to you, and I'd like to welcome you in our webinar and welcome to our university and Bangladesh also.
Thanks a lot. It's a great pleasure to be here. I think this is really a great initiative.
It's my honor actually to host you in our webinar. So you have already come to know that we have arranged a series of webinars. And in that continuity, today we have one of the greatest particle physicists and cosmologists in the world, Dr. Valerie Domcke, as a main speaker. So we have divided our webinar into three parts. First, I'd like to introduce our speaker with all of you. Then our speaker will deliver her speech with you. And at the end, we have a discussion session where anybody can join with us. So let's go to our speaker description. So you have already came to know about our today's lecture, the title, The Snapshot from the Early Universe, CMB and Gravitation. And our speaker is Dr. Valerie Domcke, a faculty member, Department of Theoretical Physics, CERN, Geneva, Switzerland, and EPFL, Lausanne, Switzerland. If we see her academic and career experience, we can see previously she worked at Dutch electron synchrotron, DESI, Hamburg, Germany, as a junior faculty member in the theory group. And in 2015 to 2017, she worked as a postdoc fellow at APC, Astroparticle and Cosmology, funded by the Paris Center for Cosmological Physics. And from 2013 to 2015, she worked at SSA, Trieste, Italy, as a postdoc researcher. And in 2013, he worked at DESI electron synchrotron, DESI Hamburg, Germany, as a postdoc researcher in the DESI theory group. And in 2011 to 2013, he worked at a DESI group as a doctoral student. And in 2009 to 2010, he was in Max Planck Institute for Physics, Munich, Germany, as a master's student. And she completed her master's thesis on the theoretical elementary particle physics and cosmology, and her supervisor was Dr. Stephen Antus. So in 2005 to 2010, she were in Technical University of Munich, Germany, as a graduate student. So if we see his research interest, if we see her research interest, she has interest in cosmology, neutrino physics, astroparticle physics, gravity, extension of standard model of particle physics. And if we see her publication list, she has a lot of publication all over the world and different journals. And we can see her ORCID ID, and this is her Google Scholar ID and Inspire Help ID. So thanks all of your question. So actually we feel proud to host her in our physics webinar. So I'd like to welcome you again, madam. So this is your time. You can start your session.
Okay, thanks a lot for the very, very kind introduction. So without further ado, let's go to the presentation. So the title of my talk today is Snapshots from the Early Universe. And what I want to say with that is kind of displayed in this little picture below. So essentially on the left, you have kind of an artist's image of what maybe the universe looked like many, many billions of years ago when it was very young. And then to kind of understand better the universe at these very early times, what we kind of want to do is we want to take a picture of this universe, right? We want to develop the picture, and study the picture, and have some fantastic ideas, right? Like develop the, whoa, this was not supposed to happen? Okay. Yeah. Okay. Like, for example, the standard model of particle physics. Now, of course, the problem with this picture is that there were no human beings around or no intelligent observers around who could kind of take pictures at the very early universe, right? That would make our job a lot easier. So we have to improvise, and we have to kind of find mechanisms, kind of physical processes, which kind of can act as a photo camera at different stages of the evolution of our universe. And this is what I'm going to talk about, and the two examples that I will use is the cosmic microwave background and gravitational waves. So what do we know, or we think we know, just to get us on the same page, the history of our universe in a very, very simplified way. So the universe as we observe it today is pretty cold, 2.7 Kelvin. It's very empty. I mean, sure, there's stars and stuff out there, but mostly it's just nothing. It's pretty inhomogeneous. I mean, here in my office, universe looks quite different than in outer space. Matter, as we know it, consists of nucleons, electrons, neutrinos, and photons. And the universe, as we see it, is expanding, which we can see by looking at the redshift of stars. Now, however, kind of the idea now is that the universe was not always like this, but essentially from the fact that the universe is expanding, you can kind of think backwards and say, well, okay, that means that in the past, as we go backwards in time, it needs to be compressed. And what happens kind of when you compress something or expand something, you know, for example, if you've ever pumped air into a bicycle tire, kind of as you compress a gas, it gets hot, right? As you expand the gas, it gets cold. So as we go back in time, we expect the universe to be a lot hotter than today. So we expect very hot universe, some crazy number of 10 to the 20 degrees Celsius, a homogeneous plasma of all elementary particles that we know of, and also the ones that we don't know of. And this epoch, we think, took about 13 billion years. So now the question is, how do we know this, right? Where does it, okay, we have the hint that the universe is expanding, and from this we can postulate this rough picture, but we'd like to know more. So my colleagues from Berkeley have made a much, much nicer version of this plot, right? So again, you have time on the x-axis and essentially the expansion of the universe on the y-axis. We start here at the Big Bang at very early times with kind of a hot, dense universe with all sorts of elementary particles floating around. And then as the universe expands, it becomes more and more like the universe that we know today with galaxies and stars and human beings. And essentially, these different slices are kind of when kind of really distinctive things happened in the evolution of our universe. And in particular, in this talk, I want to talk about this slice, which is the decoupling of the cosmic microwave background, and these very, very early times, which we hope we will in the future be able to probe with gravitational waves. So first, we need to, in order to get there, we need to first look at some more recent history. So let's go back to the 60s and to the US East Coast. So at the time, there were these two gentlemen here, Arno Penzias and Robert Wilson, and what they were working on was a radio telescope with kind of fantastic sensitivity for the time, because the goal was to enable communication across the Atlantic. So the idea was that you would have kind of this balloon type thing floating above the Atlantic Ocean. And then you could kind of communicate from Europe. You would kind of send radio waves up to this balloon, bounce them off the balloon, and they would kind of come back over here in the US, and then you could communicate between Europe and the United States. That was kind of the idea. And to do that, you needed a radio telescope, which was just much better than anything that they built at the time. So they built this device, which was kind of a revolution at the time, and they turned it on, and they had this continuous background noise. And so whatever they did, they could not get rid of the background noise. So the antenna was not performing as well as they thought it would perform, as they had computed that it would perform. So they started investigating, right? So where suspicion was, well, maybe, we're too close to New York. New York at the time was still already kind of noisy. Maybe this is contaminating our measurements. Maybe it's some solar physics which we don't understand, some solar flares which somehow emit in the radio band. Maybe it's something to do with the galaxy. Some physics in the galaxy that we don't understand emitting radio waves. But all of these explanations you can very easily exclude, because you can kind of point your antenna in different directions and see if the signal changes, right? If the amplitude of the signal, for example, correlates with the position of the sun. And what they saw is that nothing, right? This background noise that they have, was kind of really isotropic, the same in every direction, at every time of day and night. It would just not go away. So kind of a very hot candidate for explaining it was pigeons. So they went to great effort, and they cleaned out all the pigeon poop that some nesting pigeons has left in the antenna. And I think they even shot the poor pigeons responsible for it. But the noise was still there, right? So they were still stuck with this noise. At the same time, only about 60 kilometers away in Princeton, theoretical physicists were discussing kind of nearly philosophical questions about the very nature of our universe. And the two competing theories at the time were kind of the steady state universe or the Big Bang universe. So steady state essentially says, well, the universe is as it is, and as it kind of was always there in the past and will kind of always be there in the future. Nothing really changes. And the Big Bang theory was that essentially what I showed on the previous slide, that kind of there was some initial phase of the universe was much smaller and hotter, and then it kind of expanded, right? And the name Big Bang was in fact coined by the steady state people, because they wanted to illustrate how ridiculous this idea was that kind of the universe started in this Big Bang, as they called it. But these Big Bang people, here I give the pictures of maybe the three most well-known people, Dicke, Peebles, and Wilkinson. They had a very clear prediction, and they said, well, if the universe really was hotter at very early times, then there should be a background radiation coming from this kind of young universe, and that should be still detectable today. So to go into a bit more detail, the idea is the following. So at very early times, temperature was very hot, and it was in particular above 0.3 electron volts, which is the binding energy of hydrogen. So at that time, we just had protons and electrons floating around freely, so many, many charged particles, and that meant that photons, or the particles of light, could not travel freely. They would kind of be rescattered constantly, and they were kind of trapped in this plasma. But then, as the universe cooled down and it goes below this energy scale, the protons and electrons get bound into hydrogen atoms, which are neutral, and the photons can now propagate freely, because now they only see neutral particles. And hence, we should essentially see a radiation of precisely this energy kind of expanding out into the universe, which suddenly became transparent. And then, of course, we have to take into account that in an expanding universe, also kind of the wavelength of these particles get kind of stretched, get redshifted, as we say. So correspondingly, when we observe this radiation today, it will be at a lower energy compared to when it was initially produced. But we can compute, if we know the expansion of the universe, we can compute exactly kind of what to expect here. And one of the exciting predictions was that it should be in the microwave region today, meaning at the frequency of radio telescopes. And this was, in fact, precisely the background noise that Penzias and Wilson had simultaneously found when doing a completely different experiment. So in fact, Peebles and collaborators were actually kind of thinking about how to design an instrument which could make these measurements when they became aware that this measurement had actually just been done, even if those people were not actually looking for this thing. So this is kind of really one of the things that really kind of were quite spectacularly confirmed or supported this idea of the Big Bang theory for the universe. So now we know, of course, since then a lot of time has passed, right? So since then we had, for example, the COBE satellite in the 90s, and what you see here is essentially this radiation, so this black body spectrum of this primordial radiation intensity as a function of frequency, as measured. The blue is essentially the prediction, right, with one free parameter, which is the temperature, and the red are the data points from COBE, and this band down here essentially illustrates the early measurement by Penzias and Wilson. So they were kind of a low frequency tail of this black body spectrum. So now we know the spectrum very well, right? We know it's a black body radiation at 2.7 Kelvin, which sets the temperature for the universe today, which tells us that if we compare this to the 0.3 electron volts of kind of the emission of this radiation, it means that the universe expanded by a factor 1,000 since the decoupling of the cosmic microwave background. And up until fairly recently, up until last year, I would always kind of complain that the Nobel Prize in '78 went to Penzias and Wilson, and for a fantastic experiment, but despite that, they didn't realize really the significance in terms of kind of theoretical interpretation, and the theorists kind of went empty. But actually, 2019, finally, Peebles received a Nobel Prize for his contributions to theoretical cosmology, and I think this is clearly one of the biggest contributions that he made, and it really revolutionized our way of thinking about the universe and about physics. So this is kind of the first snapshot of the early universe, but it only gives us one parameter, right? It only tells us, I mean, it kind of supports this Big Bang theory idea, but the only real number that we can get out of it is this number here, right? Is the temperature of this black body spectrum. So if we want to know more, we need to kind of look closer. And in particular, one can already expect that the primordial plasma was not completely homogeneous, because if it were completely homogeneous, if you take a completely homogeneous gas and you cool it down, it just stays completely homogeneous. So we would not see stars, we would not see galaxies. So we already know that we need some teeny little inhomogeneities, some seeds, which then kind of, as they evolve via gravitational collapse, can kind of source the stars and the galaxies and the structure we see in the universe today. And in fact, this was measured then by the WMAP and by the Planck satellite. This is the most recent picture that we have. So here we have essentially, this is a picture of the sky. And this essentially shows deviations from this isotropic 2.7 Kelvin black body spectrum, right? So at the level of about 1 in 10 to the 4, you see teeny little hot spots in red and cold spots in blue. Meaning that the plasma wasn't perfect, didn't have the perfect same temperature everywhere, but there was like teeny fluctuations in this temperature at different points in space. And this is consistent with the fact that we see galaxies, that we see stars. So now we can do some mathematics, right? So we can do a statistical analysis of this picture, essentially computing the 2-point correlation function. So we take arbitrary pairs of points with say a fixed distance in this plot, and we see kind of do I end up with a correlation? So do I kind of tend to have hot spots or cold spots on both sides or not? And then you get this, right? So this is the temperature 2-point correlation function of the temperature fluctuations as a function of the angular scale, right? Where the angular scale essentially means some fixed distance in this plot here. And now the red points are the data points by the Planck satellite, and the green curve is essentially what we call now the standard model of cosmology, which essentially predicts these temperature fluctuations. So what does this prediction depend on? So it depends on, like, in order from kind of the idea that we had before to arrive at this picture here or this picture here, the things you need to know is the eigenfrequencies in this primordial plasma, the initial conditions for these teeny perturbations, because they have to come from somewhere. Then we need to know how much expansion did we have since the CMB decoupling, right? This I essentially already get from the homogeneous component. And then we need to know if there was any rescattering of the CMB light since the decoupling of the cosmic microwave background. And we can relate these 4 things essentially to fundamental model parameters. So the eigenfrequencies are given once you know the baryon and photon density in this plasma. For the initial conditions, this would kind of be a whole new talk by itself. This is set by a model that we call cosmic inflation, which describes a very, very rapid expansion, extremely early universe, and essentially relates these perturbations to quantum fluctuations. To understand how much expansion we have, we need to know the total energy budget of the universe. And to understand the rescattering, we essentially need to know how much hydrogen was reionized through stars, essentially the time of star formation, if you want. So in total, if you take all of these together, and then inflation, for example, is 2 parameters, here you have 2 parameters, so in total we end up with 6 parameters. And with these 6, so this green curve here is a function of 6 parameters. And now if you had, say, 6 data points and you model with 6 parameters, you can always make it fit, right? But here you have hundreds of data points and only 6 parameters. So it's very, very non-trivial that this works, right? So this is really, really telling you you're doing something right. And so to illustrate this, here you see the black curve is essentially the green curve from the previous slide, right? So this is kind of the standard model of cosmology as we know it. And the blue points here are the data points again, now from WMAP, so the previous satellite. And the black curve is the same in all panels. And what these colored curves are is now that I vary some subset of these 6 parameters. So here I vary, for example, the total energy budget, right? And I get this red curve, and you clearly see how this doesn't match at all, right? And then here I vary the fraction of the baryons. Here I vary the fraction of what we call dark energy. Here I vary the time of reionization. And so this just illustrates that this curve, these observations are clearly enough to pin down all of these 6 parameters. And what came out of this analysis, and this was very surprising at the time, is that actually we don't have a clue about the universe that we live in. So only 5% of the energy density, the total energy density, is made by what we call ordinary matter, right? So this is, well, everything that you see around you, right? Photons, protons, neutrons, atoms, galaxies, human beings, everything, right? I mean, this is just 5% of the total energy budget. A quarter of the total energy budget is what we call dark matter. So this is something which interacts gravitationally, right? So it pulls stuff together. But we don't know what it is. We call it dark because we can't see it. And then there's something even more mysterious, which is dark energy. And this is something which essentially all that we know about is that it is an expanding force, so it drives the expansion of the universe. That's how we know about it. But we really don't know what it is at a fundamental level. It's a big, big puzzle. So the CMB, these anisotropies in the CMB were kind of the second snapshot with now very good resolution, teaching us all sorts of stuff with quite a few surprises. So I mentioned very briefly before that these anisotropies also kind of work as seeds for galaxies. And I don't want to go into detail here, I just want to show you this picture, this little movie. So what you see here is this in the blue is essentially astronomical surveys, which kind of as a function of the distance, right, which is essentially on this radial direction, show essentially the distribution of stars and galaxies as they are measured. And this in red is essentially a simulation where I start with something which essentially looks like this picture. Okay, so I start with something which is a very good approximation of homogeneous gas, but has some teeny fluctuations at the order of 10 to minus 4, right? Given by kind of obeying the statistical properties of this 2-point function that we just saw. And then you evolve with time. So here I show, kind of, this is not the full millennium simulation, that would not run on my computer, right? It's just a small little box. And you see that kind of as time evolves, gravity pulls together matter, so kind of existing little overdensities grow, sucking in overdensities from around them. And then you kind of end up with something which, well, if you squinted it, kind of already, you can imagine this kind of looks like the filament structure that we see in the sky. And so in red, you have the output of the full millennium simulation. And of course, this is only statistical analysis, right? So you won't be able to say, this fluctuation was responsible for this star today. But you can see that just kind of squinting at this, the structure here looks very much like the structure here, and vice versa here and here, right? So at the statistical level, this idea really explains where the galaxies and stars came from. Okay, so now the last thing I want to talk about is how do we go on, right? How can we push our understanding to even earlier times, right? So way to this. So far we've talked essentially about this slice, right? This slice is the galaxy formation, right? About 10 to the 9 years after the Big Bang. This slice here is the CMB decoupling. This is about 10 to the 5 years after the Big Bang. But if we want to go earlier, we have a problem because I explained to you that before the CMB decoupling, the universe was not transparent. So we cannot use photons to probe anything here because they just rescatter, right? So we need a more weakly interacting messenger to learn about these very early times. And one such messenger are gravitational waves, right? So they are, it could be if they are emitted with a sufficiently strong amplitude at very, very early times, they just don't care about the universe at all, right? They just travel freely, they do their thing. And in principle, if we can detect them today, we can probe these very early times. Now, the problem, of course, is that precisely the property that they interact so weakly and they just don't care about what's going on in the universe here, this, of course, also means that they are extremely difficult to detect, right? Because they also interact very weakly with any detector that you try to build. So what we have seen recently, right, in 2015 by LIGO was what we call a transient event. So there was the merger of two black holes, which took place 1 billion years ago, which, on the cosmological, like on this log plot, this is nothing, right? I mean, this would be here, right? Very late times. Because in order to have the black holes, you first need to form the stars. But the merger of these black holes essentially led to a signal in here, the amplitude of gravitational waves as a function of time, which was observed by LIGO in the US and Virgo in Italy. And this kind of confirmed the prediction by Einstein that gravitational waves exist and that we actually can detect them. So now we want to go further, right? And we want to probe gravitational waves, which are not coming from these black hole mergers, but which come from even earlier, right? Really come from the very early times of our universe. And the issue now is, of course, that we don't know exactly what the universe looked like at these very early times. So in the minimal model, there are gravitational waves produced in a very early universe, but they have a very small amplitude, and they will be essentially impossible to detect with, well, for sure, the next generation of detectors and even beyond. But there are many, many models of theoretical particle physics which are kind of built to solve some open problems in cosmology or particle physics, which do predict strong gravitational wave signals. So by essentially looking for this, one can then either kind of exclude or support these types of models. So to give you some examples, if you had a phase transition, so phase transition is something where essentially your equation of states changes fairly suddenly, right? So for example, when you boil water, you go from the liquid phase to the gas phase. So this can happen through essentially spontaneous symmetry breaking of gauge groups or global groups in quantum field theory, and this would give you a strong signal. You could even, in such a process, you could form what is called a topological defect. So these are kind of semi-classical objects in quantum field theory, and they also emit gravitational waves. Also, during this epoch of cosmic inflation, which is this very, very early epoch, you produce quantum fluctuations of scalar fields, but also of tensor fields, and this also leads to gravitational wave production. The amplitude, in all these cases, the amplitude kind of depends a bit on your choices of your model parameters. So in most of these cases, you can choose the parameters such that you get a signal which you can hope to observe, but you can also kind of reduce the parameters and if nature is just not nice to us, then it will just be very hard to find these things. So I think, there's many open questions out there. And I think what we're hoping for is essentially to see a mystery noise, something that kind of is not predicted by the simplest models, appearing in these gravitational wave detectors, right? Essentially, so what we're hoping for is essentially that their sensitivity is not as good as it was calculated, and then that we can kind of go through this process that we went through for the CMB and learn something new about our universe. So the essentially next generation of telescopes for this purpose will be LISA. So this is an approved mission from the European Space Agency. Now also, I should add here, with NASA has rejoined. And essentially these are going to be 3 satellites, 2.5 million kilometers apart, exchanging laser beams in between them. So the same kind of construction in principle as LIGO, right, which is also Michelson interferometer, but now in space and not on the ground. And it's due to launch in a couple of years. And, well, 10 years. 10 years, okay, maybe more than a couple. And just to give you an illustration, of the size of this thing, so here you have the sun, and right, you have the Earth, and this is the moon, right? So, I mean, this is just huge. Also for ground-based detectors, there's kind of proposals for the next generation. So in Europe, the proposal is called the Einstein Telescope. In the US, it's called the Cosmic Explorer. So for the moment, these are not funded, so these are ideas, but it would be very nice to get something in this direction. So with that, I come to the end, right? So the points I want to emphasize is that the discovery of the cosmic microwave background has really revolutionized our understanding of the universe. And this was just kind of one snapshot in this entire picture. And I think we live in exciting times. Kind of the question is kind of what will the next snapshot bring, right? My bet is that it will be gravitational waves, and what will we learn from that? And I would very much hope that whatever we learn will be nothing that I talked about today, because it will just be something completely new that we haven't thought about yet, and it will need a new generation of physicists to figure out what's going on. Thank you.
So thank you, madam, for your wonderful session. So now, actually, if you allow us, so we can start our discussion session, and
Sure.
we can take question. So we have got one question: how can we calculate the total energy of the universe theoretically when Big Bang happened?
The total energy of the universe, was that a question? Okay. Well, this is
total energy of the universe.
So this is essentially this plot here, right? So, or let me go maybe to this slide. So in order to make this prediction, you need to, so what are you doing here, right? So here you essentially, you're saying you have an initial plasma with small homogeneities, right? And now you want to essentially compute what is the satellite going to observe today, right? So you're making a prediction about the temperature fluctuations as observed today, right? So billions of years later. And in order, one parameter that enters this prediction is the amount of expansion that we had from this early time until essentially this picture was taken. Essentially you can, which is essentially the amount of redshift that you've had in the photons, right? And now in order to theoretically, what theoretically determines the amount of expansion is essentially the total energy budget of the universe. So this is essentially, at this point, it's just a free parameter, right? And you don't know, right? But then essentially, you see there's only one value of this parameter, which essentially makes this curve here fit to the data, right? So you can, I think this is this one, right? This first. So here, essentially, in some units, I've varied the total energy density of the universe. I've reduced it by 70%. And then I get this red curve here, right? And you see, it doesn't fit the data, right? So you could have written down a model with this value, but it just wouldn't match the data.
So thank you, madam. We have another question. So how do we know there's nothing other than matter? Dark matter,
very good
and
question.
Dark energy?
So essentially, well, Okay, so it's essentially. Okay, so a lot. The question is what else could there be, right? Because we don't know what is dark energy, and we don't know what is dark matter, right? So dark matter could consist of many different types of dark matters, right? It could be entire dark sector, and there could be whatever dark humans and whatnot, and we would never know at this point, right? All we know, this is something we can't see, and it interacts gravitationally. So essentially, what determines these different components here, dark matter versus dark energy, is how they behave in an expanding universe, right? So dark matter is essentially behaves similar to ordinary matter in the sense that if you put it in a volume and you kind of you expand the volume, then the number of particles stays the same, so it means the density goes down. And dark energy has this weird property that if you expand the volume, the energy in this volume just stays the same, right? So you're producing energy out of nothing in some sense, right? This is why it drives the expansion of the universe. So essentially, if you were to postulate a new component, what would make it new is that you would kind of need to kind of give it some new behavior in the expanding universe, right? So, for example, another thing that we have is radiation, right? Radiation dilutes even faster than normal matter, right? But this is already accounted for in this ordinary matter block, right? So you would really need to write down something which is really, really strange properties in an expanding universe. And then you need to see if this is a solution of the Einstein equations, right? So here, all these things are solutions of the Einstein equations, and together they kind of suffice to explain the data. You can never actually say that you've proven a model, right? We can say this model is consistent with the data. It doesn't mean that there cannot be another model which is also consistent with the data. You can always only disprove models. You can never confirm them.
Thank you,
So
madam.
to answer the question, we don't have any indication that there's anything else, right? This is sufficient to explain the data, but we should always be open for surprises.
Okay, thank you, madam. So is there any relation between cosmological constant with dark energy?
Right. Yeah. This is exactly the same thing. Cosmological constant is just a name for dark energy. So the cosmological constant is the way the dark energy appears in the Einstein equation.
Okay, so we have another question. Why does the shape of the galaxies are different?
So why different galaxies look different? Well, I mean, if you look at this, I mean, essentially you start with these teeny fluctuations, right? But they're not like, I mean, they have these statistical properties, but it doesn't mean that they're exactly the same everywhere, right? So different fluctuations will look slightly different. I mean, as you can also see in this plot, well, this is, maybe we need a better resolution here. This really just kind of depends on kind of the teeny, what does your local environment look like at a given point? How does it collapse together? And this will kind of give you the different sizes of the galaxy. And then it also kind of depends on how exactly the star formation happened. All these, was there, for example, a supernova explosion? How old is the galaxy? These type of things.
Well, thank you, madam. So there is another question. What is the actual color of the galaxy?
What is the actual color of the galaxy?
Color of the galaxy. So maybe, he maybe indicate this picture. There is a, or I don't know why. So the actual color of the galaxy.
Well, I mean, okay. So this is essentially maybe if you observe it with a telescope, right? Essentially, the galaxy will emit at many different frequencies. So essentially, the color that you perceive a bit depends on what telescope you use, right? So we know, for example, that galaxies emit in the optical range, right? Which is when we look up to the sky, we kind of see them as white or something, right? But actually, they emit in a broad range of frequencies.
Okay, thank you, madam. So why did the antiparticle disappear? Because after Big Bang there is a particle symmetry.
Yeah. Excellent question. Okay, so what happened? Well, what we think that happened is that indeed in this very early phase, you had particles and antiparticles, right? And naively, you would think, well, if this is a thermal plasma and things are just kind of generated from this Big Bang, you would think you should have the same amount of particles and antiparticles, right? And then they would annihilate, and you would be left with essentially nothing, right? Or maybe a very small amount of particles and somewhere else some very small amount of antiparticles, right? But we don't see particles just kind of freely around, right? We don't see stable antiparticles. And so for some time people thought, well, okay, maybe we live in a patch of the universe which is dominated by particles, and there's some other patch of the universe, right, which is dominated with antiparticles, right? And maybe there's some anti-humans there or something like that. But we have absolutely no indication for that, right? Because you would expect that essentially at the borders of these different patches, the particles and antiparticles would annihilate again, and you would see radiation. And we don't see this radiation anywhere, right? So our current understanding is that there was some teeny, we call it CP asymmetry, so some teeny imbalance between particles and antiparticles in the very early universe. Essentially, this is something that essentially if you build a particle physics model at very high energies, you essentially need to include some coupling, which is asymmetric in the sense that it produces slightly more particles and antiparticles. And then, but really a teeny amount, right? On the order of 10 to minus 10 or so is the difference. And then most of these antiparticles and particles annihilate, right? And you just end up with radiation, hot plasma. But there's a kind of a teeny amount of particles that survive. And those are the particles that we observe today in our universe. So the mechanism behind this is called baryogenesis. But we don't know exactly. There's different models on the market. We don't know exactly. None of them has been experimentally verified. I can't hear you anymore.
So there is another question. So can we call antimatter is a dark matter?
No, we cannot. And the reason is that dark matter is really something that we can't see, in the sense that it doesn't interact with any particle that we know, right? Because otherwise we would have seen it, right? That's why we call it dark. And if it were antimatter, it would be very easy to see, right? We would just have to send the corresponding matter particle, it would kind of annihilate, it would give photons, and we could observe the photons. And we clearly see this is not happening.
Thank you, madam. So we have another question. So is the matter that we just have no equipment to detect the things or whatever other than ordinary matters? So so we call them dark matters.
In some sense, so I mean, we know that the dark matter, we know that it interacts extremely weakly, right? We don't know if the interaction is zero or not, right? Because it's hard to prove that. We know it interacts gravitationally. We don't know if it has any interactions kind of beyond that. And people are constantly building bigger and bigger detectors in the hope to see some very rare interactions. But so far there has been no positive signal from that, right? So in some sense, yes, right? In some sense, this distinction of calling it dark matter is in some sense our inability to build the correct detector to see it. Yes.
So thank you, madam. So we have another question. How important role does chaos theory play in the modeling of the explaining of the universe? Since we see that super teeny fluctuation eventually cause the formation of gargantuan galaxy.
Well, so how you model this is in large n-body simulations, right? So in deterministic simulations. So you really just kind of take. So essentially, what is important for this modeling is actually only the dark matter, right? Because the dark matter is 5 times more important than the ordinary matter. So the ordinary matter actually you can essentially neglect. So what people do is they essentially take some essentially dark matter particle, right, of a given mass, and you put many of them in kind of your box, and then you simulate how they evolve under gravitational interaction. So in this sense, it's a completely deterministic system. Of course, you only know kind of the statistical properties of the initial conditions. So you either have to run the simulation kind of many times, or you kind of have to look at kind of different parts of the simulation. And you need to understand that kind of any output that you get from the simulation is only of statistical nature, right? You cannot kind of predict exactly where. You cannot say, okay, I expect to see a star here and I expect to not see a star over there, right? That doesn't work. You can kind of only make say things about statistical properties.
Thank you. So we have another question. What do dark matter obey the physical law of the universe?
So I mean, dark matter. So the way dark matter behaves is really like essentially a gas, an ideal gas, right? You can imagine dark matter as an ideal gas. So meaning a gas of massive particles which have absolutely no interaction among themselves or with anybody else. And so in that sense, you can describe it with the standard ideal gas equation, and that works very well, right? It's in agreement with all observations.
Okay, thank you, madam. So we have another question. What are the odds of WIMS being CDM candidates? Can we throw the same light on the Faleron process?
Okay. I see here somebody who has some background knowledge already. So to the first question with the WIMPs, so the WIMPs are weakly interacting massive particles, right? So this is essentially a candidate for cold dark matter, which has the property that it interacts kind of at the same strength as the weak forces that we have in the standard model. So if you had asked me that question a couple of years ago, I would have said, yes, I would put all my money on this, right? Now, experiments are getting stronger and stronger and stronger, and we have not seen anything. So there's still some room, right? But it's becoming more and more difficult, right? So kind of the simplest explanations, for example, low-scale supersymmetry, are kind of being ruled out now. So I wouldn't say it's dead yet, but it's well, you can take a positive or a negative attitude, right? I think either we will find it very, very soon, or we will rule it out very soon. Or at least, I mean, you can always find some very contrived part of the parameter space where you have some cancellations and maybe you can still get it. But at least kind of the generic part of the parameter space is very much under pressure now. This Faleron process is related to this baryogenesis I was talking before, right? So this is the generation of you need this asymmetry between particles and antiparticles. So maybe you can, if you have a concrete question, maybe you can write an email or something, and I can explain a bit more, because I think it goes a bit beyond what I talked about today.
So maybe another question. So what's the fate of string theory?
I'm not sure I can answer this. Well, okay. So I'm not a string theorist, right?
Yeah.
But I mean, I think we don't know. I mean, I think we don't know. Well, let me put it this way: it's the only. So gravity, as we know it, right? Classical gravity, as we know it, cannot simply be embedded in quantum field theory, right? So there's a clash when you combine gravity as we know it and quantum field theory as we know it, and that's really a problem because I think Einstein gravity kind of works super well, and quantum field theory also works super well. So we don't want to give up on either of them, right? So there we have a problem. And string theory is the only known way of essentially bringing the two together. However, it's extremely difficult to test because it happens at extremely high energies, and also it's extremely hard to really make predictions that really boil down to something you can concretely test in a lab.
So thank you, madam. This may be the last question. So what is the effect of plasma on gas? Is there any effect?
So you mean today? Because today there's essentially no plasma, right? I mean, today the universe is just empty and cold. The plasma was at the very, very early times, right? And then the 90s and the plasma is essentially what source the galaxies. So that's the connection.
So thank you, madam. As is there no question? So there is no question in a discussion. So we can conclude our discussion, madam. So I would like to say thanks on the behalf of the Department of Physics from the University of Science and Technology. And we are very glad actually to host you in our webinar. So thanks again. And hopefully we will arrange another webinar with you, madam. So thanks again, and bye for today.
Goodbye.
Goodbye.